I welcome you all in this new lecture series of numerical analysis, and the first topic is the root finding. The main objective of numerical analysis is to solve complex numerical problems with the help of the simple calculation of arithmetic, to develop and evaluate methods for computing numerical results from a given data. In numerical analysis, we just not input the numbers to the computer, but rather we perform a sequence of calculations to produce a desired result. Now here our first topic is to find the root of an equation, which can be either transcendental or a polynomial, with the help of some methods. Root finding. Now root finding techniques generally divided into two categories. The first one is root enclosure method, simple enclosure method. Or direct method, and the second one is iterative method or fixed point iteration. Fixed point iteration scheme or iterative methods. Iterative method. So here we have two methods. One is the simple enclosure method, and or you can say the direct method, and the second method is the fixed point iteration scheme or iterative method. Now in this first method is based on the intermediate value theorem. This first method is based on intermediate value theorem. And in this method, we find an interval. In this method, we find an initial interval which guaranteed to contain the root. This first method is based on intermediate value theorem, and in this method we find an initial interval which guaranteed to contain the root, and then we will shrink the size of that interval, and we will shrink the size of the interval. So in the first method, we find an initial interval which guaranteed to contain the root, and we will shrink the size of this interval. Now in this method, in method 2, we start with an initial approximation, to obtain a sequence of approximations. Now a number small a is said to be root of fx equal to 0 if your f of a is equal to 0. This number a is said to be root of this equation if it satisfies this equation, and we also call it as 0 of this equation fx equal to 0. Here small a is said to be root of multiplicity small m if here we call this small a as a root of multiplicity small m if fx equal to x minus a power m into gx and it is equal to 0, where your g of a is not equal to 0, and in this case we will have fa f dash a f double dash a and fm minus 1 a equal to 0, but fm a is not equal to 0. So small a is said to be root of multiplicity small m if fx equal to this x minus a power m into gx, where your g is not equal to 0 and your fa f dash a up to fm minus a is equal to 0, but your fm a is not equal to 0. If m equal to 1, then a is said to be simple root. Then small a is said to be simple root. Now let us start with the method 1, which is your direct method, and this direct method involves the intermediate value theorem. So let us start with this intermediate value theorem. Let fx is a continuous function in the interval a comma b such that the product of fa into fb is less than equal to less than 0. That means either fa is positive or fb is negative, or fb is positive or fa is negative, fa is positive. So if fx is a continuous function in the interval such that this fa into fb equal to 0, then there exists at least one root in this interval AB. Now our first method is the bisection method, which is based on this intermediate value theorem, and it is basically the repeated use of this intermediate value theorem. Our first method is bisection method. This method is on repeated application of intermediate value theorem. Let fx equal to 0 or be the given equation, and suppose that and a naught b naught be the initial interval which contains your root. Suppose that this is your initial interval, so this is your I naught, which contains our root. Now in bisection method, we will shrink the size of this interval. In bisection method, we will shrink shrink the size of this A naught comma B naught. Now there are many options for shrinking the size of this interval, but here we will shrink this size by this interval by letting x naught equal to A naught plus B naught by 2. So this is my initial approximation, now which is the midpoint of this A naught and B naught. Now if f of x naught is negative, then suppose that your f of x naught is negative, and as our initial interval is this one, so we can have either f of A naught as positive or f b naught as negative. So if fx naught is negative, and suppose that your f of A naught is positive, suppose that here our f A naught is positive, that means our f b naught should be negative. Now if your fx naught is negative and your f A naught is positive, then our root lie in the interval this x naught comma A naught. So our root will lie in this x naught comma A naught, and suppose that this is your interval I1. Now again we will shrink the size of this interval. Again we will shrink the size of this interval by letting x1 equal to x naught plus A naught by 2. Now if your f of x1, say it is positive, now if your f of x1 is positive and earlier we have f of x naught negative, then our root will lie between x naught comma x1. Then our root lie in the interval I2 equal to x naught comma x1. So our root will lie in this interval. Now we will repeat this procedure until we get the desired root or any interval of very small size. So repeating this procedure, we obtain or nested set of intervals I0, I1, I2, say In, where each interval contains the root. Now let us draw the graph. Say this is your A naught and say this is your B naught, and the value of the function at A naught is positive and the value of the function at B naught is negative. So we have B naught, f B naught, and this is your A naught, f of A naught. Now we have assumed that our x naught is the midpoint of this interval. Say this is your x naught. Now here you can see that the value of the function at x naught is negative, so we have this value. This will be your x naught or comma f of x naught. Now in the next step, our root will, as the value of the function at x naught is negative and the value of the function at A naught is positive, so our root will lie between A naught and x naught. So let us assume that this is your x1. So at x1 we will assume that our function is positive, so we have this value x1, f of x1. Now we have a small interval of size x0 comma x1. On reducing the size of this subinterval, either we will approach this point and at this point we will have the exact root, because at this point the function crosses the x-axis. So on reducing the size of this interval, we will approach at this point, or we will have a small subinterval, say like this. We will have a small subinterval which contains this root. So finally we will have a nested set of intervals in which each interval contains the root. In which each interval contains the root. This interval contains the root, this one again contains this exact root. So here we will have a nested set of intervals in which each interval contains the root. Now, after n steps, either we get a root or a small interval in having the root. Now, after n steps, at first step we have the root at x naught, which is basically the midpoint of b naught comma a naught, b naught and a naught. So this length will be your b naught minus a naught by 2. Again, this is your b naught minus a naught by 2. Again, at the second iteration, we have the root at the midpoint of this a naught and x naught. So this will be your half of this b naught minus a naught. So the size of this interval will be b naught minus a naught upon 2, because this is your b naught minus a naught by 2, and again this is the half of b naught minus a naught by 2. So that will be your b naught minus a naught upon 2 square. So after n iteration, after n steps, either we will get the exact root or a small interval having the root. Now the size of this in interval is your b naught minus a naught upon 2 power n. This is the size of this interval in. Now it has to be very small, only then we can have the root. So as this, because if this interval is very small, then we can have the exact root, then we will have the error very small. So the size of in interval is this one, and it should be very small. So let b naught minus a naught upon 2 power n is less than epsilon. So let us assume this b naught minus a naught upon 2 is less than epsilon. So from here we will have 2 power n is greater than b naught minus a naught upon epsilon. So let us take the logarithmic. So we will have n log 2 is greater than b naught minus a naught upon epsilon divided by log 2. And this is same as n log b naught minus a naught minus log epsilon upon log 2. So your n should be greater than this log b naught minus a naught minus log epsilon upon log 2. Now suppose that if the size of the interval is 1 and we have to obtain the root correct up to decimal 1 place, so our error is at the second place of the decimal. So if we have to obtain the root correct up to the decimal 1 place, then your n should be equal to, now if you put b minus a naught equal to 1, then this will be your log 1. So we will have log 0.01 divided by log 2, and if you solve this right hand side, then your n will be equal to 7. So in this case we will have to perform at least 7 steps of this bisection method to get the root correct up to decimal one place. Now if you assume the length of the interval as 1 and the error at decimal, suppose that the root is set up to decimal 2 places, so we have the error at the third place of the decimal, then our n will be equal to 10. So in this case we will have to perform at least 10 steps of the bisection method to get exact root, to get a root correct up to decimal 2 places. Now let us solve a question based on this bisection method. So let us find a root with the help of this bisection method. Perform 5 iteration of bisection method to obtain smallest positive root of the equation. The equation is x cube minus 3x minus 5 equal to 0. So solution, here we have to perform 5 iteration of the bisection method to obtain the smallest positive root of this equation. So let us assume this equation as fx equal to x cube minus 3x minus 5 equal to 0. Now if you put x equal to 1, first of all we will find out the change of sign. So if you put x equal to 1, then this is your negative. If you put x equal to 2, then again this is your negative. And if you put x equal to 3, then you can see that this is your 27 minus 14. So this is your positive. So that means our root lie in the interval 2, 3. So your f of 2 is equal to, say this is your 8 minus 6 minus 5. So this is your minus 3, and which is negative. And now if you put x equal to 3, then this is your 27. Then we have minus 9 minus 5, then this is your 13. So our f3 is positive. So that means our root will lie between 2 and 3. Now if you want to decrease this size of this interval 2 and 3, then you can take the value as f2.5, and you can see that at 2.5 maybe we will have the negative value, and at f3 we will have the positive value. So that means we can say that our root will lie between 2.5, 3. So if you wish to decrease the size of this interval, you can decrease. Then you can have the exact root in lower number of steps. But here I am taking the x0 as 2 and x1 as 3. So your, say this is your a0 and this is your a1, b0. So your first iteration will be 2 plus 3.2. So this is your 2.5. Now let us find out the value of the function at this x1. Then the value of the function is 3.125. As the value of the function is 3.125 and this is your positive, and earlier the value of the function at 2 is negative, so we can say that our root is between 2. At 2 we have the value of the function as negative, at x1 we have the value of the function as positive, so we can say that our root will lie between 2 and 2.5. So as we have the interval 2, 2.5, so initially you can take, in place of 2, 3, you can take the interval as 2, 2.5. Then we can have a small number of steps. So now this is your x1. So your x2 is equal to, now your x2 will be, your next root will lie between the interval 2, x1. So this will be your 2 plus x1 divided by 2. So this is your 2 plus 2.5, so divided upon 2. So this is your 4.5 divided by 2, and this is your 2. So this is your x2. Now let us guess the value of the function at this x2 is equal to minus 0.3593, and which is less than 0. And earlier the value of the function at x1 is positive, so our root will lie between x1 and x2. So therefore root lies in the interval x1 comma x2. Hence our x3 will be equal to x1 plus x2.2. So this is equal to x1, your x1 was 2.5 plus your x2 is 2.25, and this is equal to 2.375. Now again let's guess the value of the function at this function. So the value of the function at this point is equal to 1.27148. So the value of the function is positive. So we can say that our root lies between x2 and x3. Therefore, root lies in the interval x2 comma x3. Hence our x4 will be equal to our x4 is equal to x2 plus x3 divided by 2, and this is equal to your x2 was 2.25, your x3 is equal to 2.375, so it divided by 2 will give you 2.3125. Now the value of the function at this x4 is equal to $0.4289. Again this is positive. Now the value of the function at x4 is positive. Again we have the value of the function at x3 as positive. So our root will lie between x2 and x4. Therefore, root lies in x2 comma x4. Hence our x5 will be equal to x2 plus x4 by 2. So this is equal to your x2 was 2.25, your x4 is 2.3125, and this is your equal to 2.28125. Now let us guess the value of the function at this x5. So the value of the function at this x5 is equal to 0.028106, and again this is your positive. So we have performed 5 iterations of bisection method. So now what about the root? What is your exact root? Here we can see that our x5 is the positive and your again x4 is the positive. So that means your root next step will be, in x4 we have the value of the function positive, in x3 we have the value of the function positive, in x2 we have the value of the function as negative. So our root will be, the sum will be the midpoint of this x2 and this x5, because at x2 we have the value of the function as negative and at x5 we have the value of the function as positive. Therefore your root will be, hence our root will be your x2 plus x5 divided by 2, and this is equal to your x2 is 2.25 plus your x5 is equal to 2.28125, and this is equal to 2.265625. So this is your x. But please note that we have performed only 5 iterations. So you cannot say that this is your exact root. here you can see that in x5 and in this root we have the root correct up to decimal one place. In x5 you can see that your root is 2.28. In your x, say this is your next step, which is your x6. In here we can have the root as 2.26, and you can see that at this point our root is correct up to decimal one place. Now let us obtain the 5 iteration with the help of a table. So we not need to have such calculations. So let us solve the same problem with the help of the table. So let us construct a table. Say this is your number of steps, so this is your and say here we have an, we have bn, say this is your xn, and suppose that this is your fxn into fan. Now if your n is 0, then we have a naught, then we have b naught, then your first step was your x naught, and the value of the function at x naught was 2.5, and at if you put n equal to 0, then this will be your fx naught into fa naught. Your a naught was 2, this a naught was 2, and your x naught was 2.5. Your x1, if you put n equal your x naught, earlier I have used the first iteration as x1. Now if you use the first iteration as x naught, then your x naught will be the average of this a naught and b naught. So that will be your a naught plus b naught by 2. So that will be your 2.5. Now this is, if you put n equal to 0, then this will be your fx naught into fa naught, and your fx naught into fa naught will be, let us guess the value of the function at 2.5. So the value of the function at 2.5 was positive. So the value of the function at 2.5 was positive, and the value of the function at 2 was negative. So we have the value as negative. So that means our root will lie between this a naught and this 2.5. Your a naught was 2 and your b naught was 3. Now at first step, now as our fa naught into fx naught is negative, so our root will lie between this 2, 2.5. So this will be your same, because your a naught is fixed. Now in place of b naught we will have 2.5, and the average of this 2 and 2.5 was equal to 2.25. So this was 2.25, and the value of the function at this 2.25 was negative. The value of this 2.25 was negative, and at 2.5 the value of the function was negative, and the value of now you can see that the value at this 2.25 is negative, and again the value of the function at 2 is negative. So this negative plus negative, negative into negative will give you positive sign. So we have positive. That means now our root will not lie between this 2 and this 2.5, because the product of this 2, the value of the function, the product of the value of the function at this 2 and 2.5 gives the positive sign. So now our root will lie between 2.5 and 2.25. So our root will lie between 2.5 and 2.25. So this is your fixed. So let us replace this 2 by 2.25, and here we have 2.5. Now the average of these two was this 2.25 and this 2.5 was 2.375. Now again the value of the function at this 2.375 is positive, and the value of the function at this 2.25 was negative. So again we have negative. The value of the function at this 2.25 was negative. The value of the function at this 2.375 was positive. So our root will lie between this 2.25 and this 2.375. So in next step, we have the value of the function at 2.375 as positive, the value of the function at this 2.25 as negative. So in next step, our root will lie between this 2.25 and this 2.375, and the average of these two was 2.3125. Now the value of the function at this 2.3125 was positive, and the value of the function at this 2.25 was negative. So again we have this negative sign. Now again our root will lie between this 2.25 and this 2.3125, and the average of these two was 2.28125. And again the value of the function at this point is positive, and here we have the value of the function as negative, so this is here less than 0. This is your 2.8125. Now in next step, so here the value of the function at this point is positive, and here the value of the function is negative. So our root will lie between this and this. So again the average of these two was this x2, and this 2.82125 was your 2.265625. So this is your x. Now here you can see that we have performed 1, 2, 3, 4, 5 steps, and in the 6th step we have the answer. So after performing the 5 iteration, our root is equal to 2.265625. Now our next method is Regula Falsi method, and we will also discuss the second method. So we have the Regula Falsi method and second method. In this method, we replace our curve by a chord joining the end points. So this is your A naught, and here we have F A naught. So this is your V naught, and we have F B naught. There is no need to have this sign. Okay. Now the exact root is this one, because the function crosses the x-axis at this point, so this will be our root. But here we replace this curve by a chord joining these 2 points. So this is our chord. Say this is your A and say this is your B. Now our exact root is this point, but here we replace the curve by this chord, so our approximate root will be this one. So if this is your A naught, this is your B naught, then this will be your x1. So your x1 is this point. So we have done a mistake in positioning the exact root. So that is why we are calling this method as false position method, because our exact root is this one and we have assumed this approximated root. So now let us guess the value of this x1. Now equation of chord joining this A naught comma F A naught and x naught, say B naught comma F of B naught, is given by, say, y minus F of A naught equal to f b naught minus f a naught, b naught minus a naught into x minus a naught. Now the point at which the rod crosses the x-axis will have y equal to 0, and at that point we are assuming the value of x as x1. So at this point, say A, B, say this is your C. At C, our x will be equal to x1, and at this point our y will be equal to 0. So this is equal to f of a naught equal to f b naught minus f a naught upon b naught minus a naught into x1 minus a naught. So from here we have minus f a naught into b naught plus a naught into f a naught equal to this x1 into this bracket x1 into f b naught minus f a naught, then we will have minus a f b naught plus a naught f a naught. So you can see that this term is cancelled. So this is equal to, so from here our x1 is equal to a naught into f b naught minus b naught into f a naught divided by f b naught minus f a naught. So this is your x1 after one iteration. Now if the value of the function at x1 is negative, say this point, say this is your d, then at b naught we have the value of the function as positive, so our root will lie between this d and b. So again draw chord. So we have this chord AD, BD, and now in the next step our root will be this point. Say this is your x2. Now again performing the same procedure, let f of x1 is negative, then our x2, now then our root will lie in the interval this x1 comma b naught, and our x2 will be x1 f b naught minus b naught f of x1 divided by f b naught minus f of x1. So this is your second root. Now continuing in this way, we will move towards this x2. Now suppose that this chord crosses the curve at this x2. Suppose that this chord crosses this x-axis at this x2, and again this at this x2 we have the value of the function as negative. Then again we will draw chord, and finally we will approach towards our exact root, and which is this one. So continuing in this way, we will have our exact root. Now what about the second method? In second method, we do not require this condition fa into fb less than 0. So in the second method, we do not require this fa into fb, fa naught into fb naught less than 0. So we do not require this. Initially we will guess the interval, but after that we do not require this interval. Say f of xk into f of xk minus 1 less than 0. So after that we do not require this condition. Now consider the points xk comma f of xk and xk minus 1 comma f of xk minus 1 as the endpoints of the chord. Then now consider the points, then our xk plus 1 is equal to xk into f of xk minus 1 minus xk minus 1 into f of xk divided by f of xk minus 1 minus f of xk. So this is your root for the second method. Here we do not require any condition of the type fxk into fxk minus 1 less than 0. So we will just put the values of k as 0, 1, 2, 3 and so on. Now this second method fails whenever your fxk is equal to fxk minus 1. This method fails if fxk equal to fxk minus 1. Now, whereas your Regula Falsi method is always converges, but your second method fails at this point. So this is all about this lecture. Thank you so much for joining this lecture.